Think about a warehouse. It seems simple enough, right? Just boxes on shelves. But what if I told you that one of the most basic decisions, where to put a new pallet, hides a math problem so incredibly tough it can stump even our most powerful computers? Well, it turns out optimizing a factory floor is a massive puzzle, and a totally new kind of computing might be the only way to solve it.
So how exactly do we get from a cluttered warehouse to a quantum solution? Here's our game plan. We're going to start with the real-world headache on the factory floor, see how it explodes into a crazy mathematical riddle, and then we'll call on the quantum cavalry to sort it out. After that, we'll put the old and new methods head-to-head and see what this all means for the bottom line.
Okay, our story starts in a really busy warehouse, but we're not just looking at any old shelves. Nope, we're zeroing in on a specific kind, gravity flow racks. They're pretty clever, but they also create this sneaky and very, very expensive problem.
To really get this, just picture a vending machine, but for massive, heavy pallets. These racks work on a first-in, first-out principle, or FIFO as you probably know it. You load new stuff in the back, and it slides down to the front. So the first one in is always the first one out. Simple, right? But what happens when the one pallet you actually need is stuck in the middle, say, third in line?
And that's where the hidden costs just start piling up. It's a domino effect. To get to that third pallet, you have to physically pull out the first two. Now you've got a forklift operator stuck with two pallets they don't even need right now. Every single minute they spend putting those back on the shelf is a minute they're not doing productive work. This constant shuffling just burns through time, labor, and forklift fuel. It's this huge, invisible drain on the entire operation's efficiency.
So we've got this physical, real-world headache. Now let's watch it transform into a surprisingly tricky math puzzle that we absolutely have to solve.
You see, this whole problem of deciding where to put new pallets is a classic example of combinatorial optimization. And honestly, a great way to think about it is planning the seating chart for a big dinner party. Your goal is to put people who get along well at the same table to maximize good conversation, right? Well, in the warehouse, it's the exact same logic. The goal is to put pallets that are often requested together on the same shelf to minimize all that painful shuffling later.
Now, you can't just throw these pallets anywhere. The model has to follow a really strict rule book. First, every new pallet has to be assigned to one and only one shelf. Second, you can't overstuff a shelf. It has to respect the capacity. And here's the really clever part. The model isn't just looking at the new stuff coming in. It has to take into account everything that's already sitting on the shelves, using historical data to predict the absolute best way to arrange everything for what's coming next.
And this is where things get kind of mind-bending. This problem isn't just hard, it's what's known as NP-hard. What that means is, as you add more pallets and shelves, the number of possible layouts doesn't just climb, it explodes, exponentially. For a regular-sized warehouse, the number of possible arrangements is bigger than the number of atoms in the known universe. Seriously, a classical computer could run for centuries and still not find the single best answer.
So when you're up against a problem with more possible answers than there are atoms in the universe, a faster classical computer just isn't going to cut it. You need a totally different way of thinking. You need a different kind of computer. And that's where quantum annealing comes in.
To get this quantum annealer to work its magic, we first have to teach it the rules of the game. We translate our business problem into its language, which is a special equation called a cubo. Think of it like a scoring system. We define our main objective, like putting frequently used pallets together, and give that a low cost, which is good. Then, for any rule breaking, like overfilling a shelf, we add a massive penalty value. The quantum annealer's whole job is to explore all the possibilities and find the arrangement with the absolute lowest score.
All right. Now, let's put on our thinking caps for a second, because this is where it gets really cool. Imagine our problem is a landscape with hills and valleys. The lowest valley is the perfect solution. A classical method is like a hiker. It has to physically climb over every hill to explore the landscape, and it's really easy for that hiker to get stuck in a small, shallow valley, a local minimum, and think it's found the best spot when it hasn't. But a quantum annealer, well, it doesn't play by our rules. Thanks to a wild phenomenon called quantum tunneling, it doesn't have to climb the hills. It can literally pass straight through them.
And this ability to tunnel, that is the absolute game changer. It's the key advantage. By tunneling through these energy barriers, the system can escape those tempting but ultimately low-quality solutions. It allows it to explore the entire solution space and find the true global minimum. We're not just talking about a good warehouse layout. We're talking about the mathematically optimal one.
Okay, so the theory sounds amazing, right? But how does this quantum hybrid approach actually stack up against a powerful classical method when you put them head to head? Let's check out the data.
This chart really says it all. We're comparing 3 different solvers. Remember, the goal is to get the lowest score, or energy, possible, so lower bars are better. And the results are just crystal clear. The D-Wave CQM solver, our quantum hybrid on the left, finds a way better solution, a much higher quality answer, than both a generic classical solver and even one that was specially adapted for this exact problem.
But solution quality is only half the picture. The real jaw-dropper is the speed. Look at this. For the biggest, most complex version of the problem, the quantum hybrid solver spit out its superior answer in just under 10 seconds. The classical solver, it was still chugging away for nearly 15 minutes. That's almost 90 times longer, and it still ended up with a worse solution. That's not a small difference, that's a whole different league.
For any operations manager watching this, that huge performance gap isn't just some abstract number on a chart. It translates directly into real dollars and cents, real business value. And get this, the study showed that even if you could magically engineer a classical solver that was 20 times faster than what we have today, it still wouldn't be able to keep up with the quantum hybrid approach when the problems get really big. The performance jump is just that significant.
So what's the bottom line for the people on the factory floor? It means making smarter pallet allocation decisions in seconds, not minutes. It means drastically reducing those wasteful reinsertion costs, less wasted labor, less forklift time. You get higher warehouse throughput, better inventory organization that's actually based on real demand, and all of that adds up to the potential for some pretty serious operational cost savings.
Okay, last but not least, let's zoom out and put on our IT strategy hats. If you're planning for the future, for growth, how do you even begin to choose between these 2 very different technologies?
It really all boils down to a classic engineering trade-off. On one hand, you have the CQMI hybrid solver. Think of it as a high-performance service. You get incredible speed and top-notch solution quality, especially as you scale up. The trade-off is you have less flexibility. You're relying on a third-party service. On the other hand, you have simulated annealing. This is your in-house, build-it-yourself option. You get total flexibility, complete control. But the con is massive, it's so much slower, and it's always at risk of getting stuck in those good enough solutions, a problem that just gets worse and worse as your operations grow.
And here's the final verdict. For a small operation, maybe that in-house flexibility is worth the performance hit. But as your business scales, the risk of a slow, suboptimal solver becomes a huge liability. A dynamic factory floor needs the best answers, and it needs them fast. So for scaling operations, the hybrid approach really offers a much better engineering compromise. It delivers those high-quality solutions with the speed that a modern, growing business actually needs.
So we'll leave you with this final thought. The complexity of logistics and supply chains is only going in one direction, up. The ability to find the truly optimal solution in minutes instead of hours is quickly shifting from a competitive advantage to a basic necessity. So the question you have to ask is your current tech stack built to solve the problems of tomorrow, or is it already struggling to keep up with the problems of today?